Okay, so I know we did a little transition here. We just got done doing factor label, and like I said, I thought you did great. I thought you did a great job on factor label. And what we're doing in the next phase of chemistry is we start getting into matter. And as a matter of fact, you look at the chapter, it's called matter. And this is something they would do in elementary school. What is matter? In middle school, they would do it. What is matter? Do you think you know what matter is? And he said, well, I don't know. I don't know if I remember that from middle school. And so have you ever heard the definition of matter? That's where the word material comes from, isn't it? And so it's matter. And you can join. Okay. So anyway, let's take a look over here. Matter, if you look over here, it says the stuff in which the universe is composed. It has two characteristics. It has mass and occupies space. And I know what they usually do in middle school. They'll say, matter is anything that has mass and occupies space. And have you heard that? What does occupy space mean? What do you mean by occupy space? Does this pen occupy any space? Which one of these occupies more space? This one. So what's another word that you use for occupy space?
Volume.
Yes. See, he already knows that. So we know that volume is you take up space. Some books will even tell you that mass is like inertia. Inertia is a tendency of an object at rest to stay at rest. But if you're in motion, it's a tendency to keep moving. And they say mass is a measure of inertia. So if I have this calculator and I have this pen, which one has more mass? You actually can't see it, but something in your mind says, I've picked that up before and I've picked that up before, so you probably think this has more mass, right? So you wouldn't know that. Over here, you wouldn't necessarily know this because these two objects, they take up the same amount of space, don't they? But you don't really know which one has more mass. So you can't see mass, but you can see volume. And so I'd have to put this on a balance. And we'll be doing that. Our next lab has to do with that, where you do measurement lab. So after this chapter, you'll actually be measuring, and we'll be using some neat equipment. You even using a digital thermometer. You'll be heating water, filtering water. We'll be doing that after this chapter, okay? Now, so matter, chemistry is a study of matter and the changes in matter. So I guess we need to know that. Now, what I'm going to do is, here's a chart that they have in the book. I'm going to draw mine a little bit differently than yours. So I think I have, I don't have it here, but I'm going to draw a chart a little bit different than the book. And so I'm going to start here. What do you know about the states of matter? And what happens is when you're in elementary school or middle school, they like to call them states of matter. I don't know why. I don't know why. Does that make you feel like you can understand it better? What do you mean states of matter? But most of the time when you get into higher sciences, they won't call it states of matter. They'll call it phases of matter. So say, what phase was it in? Solid, liquid, gas, okay? So you probably heard of solid. I know you have. You probably heard of liquids, and you probably heard of gases, like that. Now, you may or may not have heard of another state of matter, plasma. Have you heard that? Okay, so even though I don't deal with plasma in this class, so I'll probably be doing solid, liquids, and gases. It is interesting if you want to look up that fourth state of matter called plasma. It's very interesting. But for right now, when you were in middle school or even elementary, they may have asked you some questions like this. Would you say that they have a definite shape? Do you remember this? Did you have something like that in middle school? And I'm going to go through this kind of quickly. But what they don't do in middle school is they don't ask you why. They have a chart, and you say, hey, do you have a definite shape? Do you have a definite volume? Do you have a definite volume? Do you have a definite shape? Do you have a definite volume? And they have a chart that you look up, don't you? You have to memorize. And yet they don't they're not able to stop and say, why? Tell me why. Why do you think a solid has that? And so let's take a look at the first column here. All right, have you learned this? I know you did, middle school. What do you think about it? Here's a solid. Does it have a definite shape? Watch now. Watch. Or did it change? Did it change shape or did it? Okay. All right. So we say yes, right? Now, let me ask you this question. Why? Why? Why does it have a definite shape? They don't ask that in middle school. And I'm going to have another column down here. We're going to do a concept drawing. I'd like you to draw what you consider to be, if you could see the particles, if you could see the particles that make up this pin, what would they look like? Go ahead and draw a concept of that. What do you think? And so maybe you drew something like that. Okay. So maybe you drew something like that. And what were you trying to tell me with your concept drawing? That the particles are what? They're very close to each other, right? Now, what does that mean? So what if you are very close? What does that mean? And there's a theory. The theory says that matter, when you get matter close to other matter, it actually attracts each other. And there is an attractive force between matter and matter. And so if the particles were very close, then they would actually attract each other in every direction. What would happen then if I do this to the pin? If I do this, why would it keep the same shape? Because they're still attracting each other, aren't they? Okay, so that was pretty easy. Let's jump over here to gases. Do gases have a definite shape? Well, I don't know what you mean. Well, let's take a balloon full of air. Right now it has a shape because the balloon's causing that shape, right? What if I open up the balloon? It could take on this shape, couldn't it? I could take all the air in this room and put it in a scuba tank. It would take up that space, couldn't I? Okay, so there's no way that gases have a definite shape. They can have any shape, pretty much any shape. As a matter of fact, you probably heard your middle school teacher say, takes, what do they call it? Takes the shape. You can probably finish the sentence for me, right? Takes the shape of its what? I knew you heard this. Takes the shape of its container. Have you heard that? So it actually, gases would take the shape of their container. If it's the container's this room, it takes on this shape. All right, that was pretty easy, but I want to know why. Let's go down here. Let's do a concept drawing of gas. Why don't they have a definite shape? And probably you've already figured out that relative to each other, they're pretty spread out, aren't they? There's a lot of empty space there. I actually shouldn't say empty necessarily. I guess I could. Okay, empty space. they're really, really spread out. So they're really spread out. And so think about this. You told me, or I told you maybe, that because they're really close, they're really attracting each other, and they don't let each other change shapes. They don't let you get out of wherever you're at in that alignment, that pattern. I don't let you move. Here, I can't even. They found out that when particles get even a little bit further away from each other, they don't attract each other hardly at all. There's almost like no attraction. So they're bouncing around, but there's no attraction. So there's no way they're going to keep their shape. Now, let's go down to this one. How about a definite volume? Do you think this pen has a definite volume? What if I go like this? What if I go like this? Okay, let me ask you a harder question. What about this one? What if I squash that into a pancake? Do you know a lot of people, they did a test once, and they started with kindergarten kids, went all the way to college, and asked them questions like that. They had 2 pieces of clay on a balance, and they were exactly balanced like this. And then they would take 1 piece of clay off, and they flatten it into a pancake. And the pancake was really small, but it was kind of thin. And they asked, he said, when I put that on the balance again, do you think it's going to balance again? Or do you think the pancake thing's going to make it go down? Or do you think the pancake thing's going to go up? And they did this all the way through. And even people in college missed that question. Most kindergartners missed that question because they didn't have that concept that, see this matter? See that matter right there? Even if I squash it into a smaller space, it's a solid, right? It's still the same volume. It's still the same matter. I didn't take away any clay, did I? If I don't take away any clay, I don't care what shape you put it in, it's going to balance, isn't it? And a lot of people miss that question, even people in college. Because in their head, they said, well, something's less. And some people thought, no, something's more. And in their head, they kept thinking, no, it's not going to balance. There's something different about that clay. Yeah, it had a different shape. But what about its volume? It looked like it took up more space, but it takes up the same amount of space. So if I squash this, it won't be as tall, but it'll be wider, won't it? It actually takes up the same amount of space. That's a thing called volume. What about gases? What about gases? No, because I could take the air in a scuba tank, open it up, and it would do what? Take up this much space? No, it would take up this much space. And so there's no way that, and that's the same reasoning. Hey, why do you have a definite volume? You know why. My particles attract you so much that I can't let you spread out. I can be flatter, but we're still the same distance away, and we're still attracting each other a lot. Now, I purposely left this to the end, okay? Because this is where there's a little bit of conflict here. I still think, I know there's still elementary science books, I hope not middle school, that teach this part wrong. And you probably, this is kind of like, in a way, this is baby stuff in a way, but I'm going to teach this right here. What about liquids? Do they have a definite shape? So if I had a really tall glass of water, could I put it into a big flat bowl? Would that have the same shape? No. So in a way, it acts a little bit more like a gas, doesn't it? Now, the question is, why? Why would it act a little bit more like a gas? And you say, well, I know why, and you're going to draw this, but not yet. Don't draw it yet. What about volume? If I had a really tall glass, a tall graduated cylinder, and it said 100 milliliters, what if I poured it into a fat graduated cylinder? Would it still go to 100 milliliters? Well, then it has a definite volume. Well, wait a minute. Wait now. Now we have a problem. One chart says you act a little bit more like a gas, and this one says you act a little bit more like a solid. And so I'm going to add another column here before you draw this, okay? And this is what did it for me when I finally figured out that what everybody had been teaching me before wasn't quite right. Are you compressible? Are you compressible? Now, I can make this thing flatter. I can make it flatter, but can I make it take up less space? Can I make this thing take up less space? And the answer is no. Solids are essentially uncompressible, okay? And why? Why are they uncompressible? Again, the middle school teacher might have you memorize a chart. I'm going to ask you to think about it. Why would a solid be non-compressible? Why? And it goes back to here again. there's essentially no space between the particles. They're so close together, there's almost no empty space there, get it? So you can't squeeze it. How about gases? Oh, yes, for sure. I could squeeze. Matter of fact, when they transport natural gas is, hey, I need some natural gas on the farm out there. Well, how are you going to get it? We're going to put it in a truck. Well, the truck would have to be tremendously big to give me the gas that I want, the natural gas. I don't mean gasoline. Gasoline's a liquid, right? And so what they do is they say, well, we're going to squeeze it. And they do. They squeeze the gas. See that? And they do something else. They cool it. If you cool it, that'll make it take up less space. And you squeeze it, it'll take up less space. And so they have refrigerated, compressible trucks, and they send huge, huge amounts of gas all over the country. Now, if I'm one of those drivers, I want to be safe. It would not be good if somehow I had an accident and then, and I know they make those things very, very well. They engineer them well, but that always be in the back of my mind. That would not be good if a compressible gas were to be uncompressed. If somebody shot a bazooka in there, I'd be dead. Sure. It was just as a gas escaped, it would set up a shock wave and essentially kill me like that. So let's go down here. This is an essential question right there. Can you go to the store and buy compressed milk? That would be good, because then you could take up less space, couldn't you? Can we buy compressed milk? Can you take a gallon of milk and make it take up less than a gallon of space? Wow, if they did, I think I would have heard about it. Can you do it or not? Are liquids compressible? What does that mean? Why weren't you compressible? My particles are really close. Why are you not compressible? Go ahead and draw this. Now, before you do it, I'm going to give you, here's what's the problem. Somewhere in middle school or elementary, they did this, and this is called the Goldilocks thing, okay? If a teacher says the particles of a solid are really, really close, and the particles of gas are really far away from each other, what does your mind want to say here? And what do they teach in elementary school? And what is it that you like, the Goldilocks thing, two very, very close, not very close. What are you going to say here? About halfway. Okay, that's the way they teach it. Unfortunately, that cannot be true. It cannot be true. We want it to be halfway because that's easy to teach that, isn't it? But how are you going to draw this? You better draw them really close. They are really close. And if you're a science student at all, there's one thing I said today that doesn't quite make sense. What is it that doesn't quite make sense? See? See? So, even though it's very close, it is. I know it's very close. You know why? It has a definite volume. I know it's very close because you can't compress it. But there must be at least a certain amount of distance that allows layers of one liquid to slide by the other layers. See that? Otherwise, see that? So we actually can pour. You know what fluids are? Fluids are these. Fluids, anything that can flow. And gases and liquids can both flow. You get that? But you cannot compress a liquid. Some really smart people a long time ago, they didn't know this for a long time. They didn't know that if you put a liquid in a tube and you try to compress it, if you try to compress it at one end, like this, you won't be able to compress it. But what will happen is, whatever force you put on here, it'll go all the way down to the end of that tube. Matter of fact, if you multiply that tube into 10 pieces, and you push down here, woo, all 10 of those little fingers will have the same force on them. You say, what? You mean I could push here with a little bit of force and get like 100 times my force? Yes. Well, that would be tremendous. And it's called hydraulics. What are hydraulics? How can these machines, with a guy takes a little lever and goes like this and digs out how do they do that? When I go home, I have to stop my car when there brakes. How do I do that? It's not like Fred Flintstone, right? Put your feet down. I put my foot on the brake. How's that work? There's fluid. There's fluid in the brake line, isn't there? And I'm going to try to compress it. But you know what? I can't. But what happens to that force when I try to compress the brake fluid? Vroom. It goes to my brake pads. And, vroom, vroom. And I'm actually able to stop the car. Now, what happens if you brake? If you have a leak in your brake line, or you run out of brake fluid? And you've seen all these TV shows about people that try to kill people. I hate that. And once you get rid of the brake fluid, you try to stop your car, it's not stopping. Sometimes you get brake lines that have air. They get air leak in them. They have some kind of leak. That's not good, because you get an air bubble in there. You put on the brakes, it goes, ooh, ooh. It makes the air bubble smaller, but it didn't stop your car. So you have to do this thing called bleed the brakes. You go where the wheel is, you take this little cap off, and you pump the fluid, and get that air bubble out of there. And you put the cap back on, put some more fluid in there, and then your brakes work. So anyway, it's pretty neat how we figured this out. And this right here is pretty neat stuff if you think about it. Engineers, there are engineers who are specialists in solids or liquids or gases. They specialize in it. Okay, what do you think about that? I probably won't get into this. If you want to look it up, you can. But plasma is really interesting, because if you could energize matter to the point where even its own electrons were not necessarily with its own nucleus, then you have a soup of a lot of negative particles and a lot of positive particles. See that? And that's almost like taking matter apart. And that is plasma. So, but we won't be doing that here. I have a little plasma ball, a little thing there. That's a plasma ball. And it's kind of like a form of plasma. So you can have plasma here. The sun has lots of plasma on it like that. Okay, so what I'm going to do now is I'm going to show you some words. I know. If you were to take a solid, let's get some vocabulary words down here. Liquid, gas. Let's do some vocab words. What do you call it if you were to add heat? If you added heat going this way, and you went from a solid to a liquid, what do you call that? I'm going to get some of the baby words here, but what do you call it? Melting. All right? As a matter of fact, the temperature at which that occurs is called the melting point. Right? The melting point is the temperature. For ice, 0 Celsius is the melting point of water, isn't it? It'll change from a solid to a liquid. The theory is that the particles that are really close, they're still close, but they start moving faster. It's called the kinetic theory of matter. Kinetic meaning kinetic energy. The kinetic theory of matter says if you heat something like water or ice cube, the particles will start vibrating more, and they'll actually have more kinetic energy, and they'll have a little bit more space with them, and then they'll change from a solid to a liquid. Again, only a little bit of space here. And then what would happen if you continue to heat the liquid? The liquid would get hotter, vibrate more, faster. And then what do you call it when you go from a liquid to a gas? These are kind of simple words. I'm just trying to get over simple ones. What is it? Boiling. And the temperature at which that occurs is called the boiling point, isn't it? The boiling point of water is 100 degrees Celsius. Now, at this point, the water is not only moving faster, but some of them have moved fast enough to get far enough away from their next door neighbor to have enough space that it'll actually change into a gas. Now, you also have heard that, do you know that liquids can change into a gas below the boiling point? What do you call that? Like, if I put some water right here on this desk, and I just wait, and it'll be gone. It changed from a liquid to a gas. How did it do that? It evaporated, didn't it? So you could call this, it could evaporate. You can vaporize. So some books might say vaporize. Boiling point, vaporization point, same thing. And then if we were to move this beyond, we could go to a plasma. Again, I'm not going to spend much time with that in here. But now, that's if you add heat. Let's go the other way. let's remove heat. What if you remove heat? What do you call it if a gas changes from a gas back to a liquid? What do you call that? I'm trying to do this kind of quickly because I don't want to bore you with the simple words, but have you had these words before? What do you call it when a gas changes back into a liquid?
Condensation.
Yeah. See that? So anyway, condensation, it changes from a gas back to a liquid. So you could definitely take a gas, and if you were to cool it, you could cool it, you can actually compress it, and you can actually change it into a liquid. What do you call it when a liquid is changed back into a solid? What's that called? Yeah, that's it. Thank you. Now, I will say that the word freezing is always used for water, but most people don't say that liquid gold froze. They don't like to use that, so they say solidification. Ooh, solidification. Oh, I get it. It changed to a solid. That's it. So if I had liquid gold and I let it cool, it would undergo solidification, wouldn't it? So now we have these different words here. Who knows about this? almost every material goes through the phases solid, then liquid, then gas. But we have several examples on the earth where things go directly from a solid to a gas. Does anybody remember that word in middle school? I don't think you had it in biology class. You ever heard of this? Susie, if anybody? Okay, it's called sublimation. And so something sublimes. And the best example is dry ice. It's very cold. You can make it look like a cube if you want. So people like to call it ice, but it's not made of water. Dry ice is made of solid carbon dioxide. See that? And as a matter of fact, it starts changing from this to that at about minus 110 Fahrenheit. So it's really just a little bit of heat will actually make it sublime like this. And then you get CO2 gas. All right, another one I know of, which they don't sell very much. When you guys did your insect collections, did she ever say anything about putting something in there to keep other little parasites from... There's things that get into insect collections, you know that, and they actually chew the head off, and you see a little dust pile, and you see your head of the wasp is gone. Or did she say anything like that? If you want to keep your insect collection around for a long time, okay, you can buy these little things called mothballs. Now, mothballs, if you ask your great-grandmother, I don't know if it's still alive, but your great-grandmother would know about mothballs because people bought them all the time. They put them in some socks, put them in a drawer where their sweaters are, and because they don't like moths, if moths get in your house, they would go after these wool sweaters and eat holes in them. And they do that. They can still do it today. And so they would put these things like mothballs in there. Now, mothballs, they have a smell to them, a distinctive smell. But if you just set them down and you look at them a day later, you notice they're getting smaller. I can smell the smell, but how did it change? It changed from a solid into a gas. I never saw liquid mothballs. It's very difficult. You'll probably never see liquid carbon dioxide. That's very difficult. Another thing that's interesting to me is if it snows, and you notice it snows here, and the sun's out, but the temperature's like 27 degrees Fahrenheit, you know you never got to the melting point. You didn't. For the next 2 days, the snow is less. You never melted that snow, but it looks like it's less. You know what it actually did? It actually did this. Some of it actually changed into, it evaporated. It's sublimed. All right, have you heard these words that I'm saying here? This is called the kinetic theory of matter, and that's why you see people's hands go like this a lot, like that. All right, well now what I'm going to do in the remaining time is the handout sheet that I gave you. There are some words there that there's some words on a handout sheet that we're going to be spending a lot of time on. You are, for sure. And I'm going to make a chart with some of these words. And here's sort of a chart that I got this online. And so we have some words here. Okay, here's matter. Anything that has mass and volume. We talked about that. And if you want to classify matter, and humans love this. Humans love to classify. In biology, do they like to put them in little categories? What if you're an auto mechanic and you talk about your parts, you know? What if you're a sports enthusiast? You have your little categories. You like to group things, don't you? We love to group things. We love to name groups. So it's obvious that chemistry people would say, if we want to study all of matter, we need to study them in groups. So here's one way that you could separate them. Look at this right here. Matter could be called a substance or a mixture. So then they have some different definitions down here. See that? A substance is a matter with a constant composition. And when I was your age, I know I didn't understand what they meant when they said that. So let me see if I can help you here. How many ways can you make this stuff? Only one. If you have a constant composition, there's only one way to make you. Can you remember that? If you have a constant composition, there's only one way to make you. Hey, I noticed that water is down here. Water is going to be down here. See that? Oh, water? Water is a substance? Yes, it is. And you're telling me there's only one way to make water? That's right. 2 H's and 1 O. And what about this? Oh, elements? That's right. That's right. Gold. Gold here, gold in Germany, gold in Thailand. It's gold. You get it? So we have this group of matter, which we call a substance. Some books call it pure substances. Now, don't let that worry. Most of the time, I think your book says pure substance, and then sometimes it leaves off the word pure, but that's what they mean. Everybody get that? So if you're a substance, you have to be either an element or what? A compound. Well, let me tell you this now. How do you know if you're an element? This is going to seem like a hard question, but it's incredibly easy. If you're an element, you're only made of one kind of atom. And you know where I find it? On the periodic table of the different kind of atoms. Well, what's that called? That's the periodic table of the different kind of atoms that we've ever discovered. So elements are only made of one kind of atom. Each gold is made of gold atoms. Got that? But what about this? And if you're made of one kind of atom and you're on the periodic table, I'll write that down here. If you're on the periodic table, then there is such a thing as an atom of you. Is there such a thing as an atom of gold? Yes. Atom of carbon? Yes. An atom of air? No. An atom of skin? No. Atom of water? No. There's no such thing as that. There's not an atom of wood. That W doesn't stand for wood, does it? So if you're not on the periodic table, there is no such thing as an atom of you. Is there an atom of plastic? No. Okay. Well, what about things that are combined or chemically combined? They're called compounds, aren't they? We have a whole chapter where I teach you how to write compounds, how to name them. You'll be great. You'll learn this. You'll eat this up. So this right here, like CO2, H2O, C6, H12, O6. I've seen those. That's more than one kind of atom, isn't that right? And if they're chemically bonded together, what do we call that? We know your matter, we know your substance, but what do you call that? Compound. How do you know if something's a compound? It has a formula. It has a chemical formula. These are formulas, aren't they? C6H12O6 is the formula for glucose. It's the chemical formula. I get it. Okay, so is there such a thing as a compound called water? Well, does water have a formula? Yes, it does. H2O. Then yes, the answer is yes. what about air? Air, no, it can't be that. I get it. Is there a chemical formula for air? Nope. What? If you're not on the periodic table and there's no formula for you, you must be what? See this little flow chart? If you're a pure substance, you're either an element or a compound. But what if you're not on the periodic table? And what if there's not a chemical formula? Then you must be what? What's it called? A mixture. Now, what separates a mixture from this? This has constant composition. There's only one way to make those. What about this? A mixture, there are many ways to make it. I'll give an example. Pizza. How many ways can you make pizza? How about salt water? Everybody go home, make some salt water. Bring it to you tomorrow. I'll analyze it. Will everybody make it the same or not? They won't. There are many ways to make salt water, isn't it? How about a salad? Oh. So we have lots. I would say most materials on the planet are actually mixtures. They're mixtures. You get it? Now we go over here, and if you're a mixture, that means there are many ways of making you. Get that? So now I have two new words for you. There are some mixtures, when I look at them, it's clear that they're made of more than one material. Here, I'll show you. Let's see. Where's my? Do you see a rock there? Is there a rock on my tape? I used to have a rock. Okay, I don't. Okay, how about this? What do you think? Bad example. Let's see. I need something else. No rocks. All right, how about this? This right here, this part looks like it may only be made of one material. But look at this right here. This is different, isn't it? So many rocks are actually combinations. They're actually mixtures. But sometimes you have mixtures, when you look at them, it's clear that when I see you, I can see more than one thing there. You get that? I just look at it. Look at your skin. Oh, that's a heterogeneous mixture. Hetero means other. It means you can see other things. You get that? Just like in biology. Remember heterozygous? Remember if you were like this, if you were big B, if they were the same, homo means same, doesn't it? Homozygous. Oh, somebody should have taught me that. And what about this? How about big B, little b? Not the same. That's the other one. This is heterozygous, isn't it? Hetero. Anyway, so if you're a heterozygous mixture, I can just look at you and tell that you're a mixture. Now, you got to be careful again, because a lot of people think that water is a mixture. No. There's only one way to make water, and it has a formula, doesn't it? But pizza's not. You'll never see a chemical formula for pizza. You won't even see one for air. Wait, air? When I look at air, I only see one thing. But you know what? It's not on the periodic table, and there's no formula. It has to be a mixture. But it can't be a heterogeneous mixture, because I don't see anything different. So what do you call some mixtures? When you look at them, what do they look like? They look like one thing. You see that? And that's a homogeneous mixture, and that's the word solution. So you need to know that word right there. If something is truly dissolved, when I put salt in water and I mix it, and you cannot tell that there's any salt in any water. You knew it's in there because you put it in there. If it's truly dissolved, it'll look like one material. So salt water is a mixture, because I can make it many ways, but it's a homogeneous mixture. What about coffee? Yeah, homogeneous mixture. See that? And so these are called solutions. Now, salt water is a great example. You can make that many ways. Air. Right now, the air in the corner of that room is a little bit different than right above my face. I'm giving off more CO2, more H2O than over there. So the air right above me is slightly different than the air over there. You can't tell it though, can you? And how about another one? Here's one that's kind of difficult. Did you know that you can actually put a solid and dissolve it in another solid? Did you know you can dissolve a solid in a solid? Did you know that? Now, it's a trick in a way because I have to melt both of the metals. I melt them, and then they mix, they dissolve, and then I let them cool off. And this is what's called an alloy. All right? Guess what the most famous alloy that I know all of you know about starts with an S, T, E, steel. The word steel is not on the periodic table. There is no formula for steel. When I look at a piece of steel, it looks like one material, but I know it's a mixture. So it's a homogeneous mixture, and it's called an alloy. You can make steel many, many ways. You can make steel carbon steel, nickel steel, chromium steel, stainless steel. You can make many, many kinds of steel. Another one you may have heard of, an alloy, is called brass. That's copper and zinc. Remember in history class, did they have the Bronze Age? Remember that? That's an alloy. Iron was good, bronze was better. And we made all kinds of alloys in our life. And we make some of our jet planes, titanium alloys, things like that. All right, so what I'm going to ask you to do, this is a pretty good start. This is a pretty good start on this chapter. And so what happens is, I want you to spend some time on these vocabulary words. Say, I think I understand the difference between a solution and a compound. I had a student a few years ago, they made a little practice test. And again, this is not a real test, it's more of a mini test. But the chapter has very little, it'll have questions on there, but the other part of the mini test will be factor label. So one more time, next week, probably on Thursday or Friday, you would have a mini test on chapter 3 and factor label. You get that? So you'll have one more time to show off and show me how good you are with factor label. All right, anyway, this little, this 2-page thing here, that's a student who made that up, and they thought that would help them do that. Okay. Again, sorry, I like I said, I love being here. I love here to be with you. I just have something I have to get done, and so it's one of those things. Yeah. All right. Do you have any questions for me?